Section. Introduction. We're living in an exciting era where generative artificial intelligence, GenAI, is making significant strides in image generation, particularly through text-to-image models. Current models like Stable Diffusion, DreamBooth, StyleDrop, and ControlNet primarily focus on specific instruction types such as text prompts, subjects, styles, and edges. However, these models struggle with more complex instructions that involve multiple elements, and they often fail to generalize to unseen instructions. In contrast, when humans create art, we often integrate various elements to achieve the desired outcome. For instance, an artist might start with a rough sketch, apply a specific style like Impressionism, and use photographs or live models as references. This process of image generation is inherently multimodal and complex, and it's challenging to communicate these complexities even among humans. So, how can we effectively communicate these multimodal complexities to models? To tackle this challenge, we're introducing a new approach: multimodal instruction in image generation. This method combines and adheres to information from different elements, expressing the conditions for image generation. In essence, multimodal instruction enhances language instructions by integrating information from other elements to describe the objective of generating a customized image of the given subject in the provided visual style. To implement this, we've developed a model called Instruct-Imagen. This model uses a two-stage training approach to first enhance its ability to process multimodal instructions, and then faithfully follow the multimodal user intents. Initially, we adapt a pre-trained text-to-image model to handle additional multimodal inputs, and then fine-tune it to accurately respond to multimodal instructions. Instruct-Imagen excels in merging diverse modal inputs like sketches and visual styles with textual directives, producing contextually accurate and visually compelling images. It demonstrates a strong capability of understanding sophisticated multimodal instruction to generate images faithful to human intention, even when the instruction combination has never been observed before. Our human studies show that Instruct-Imagen not only matches but, in several instances, surpasses prior task-specific models within their domains. More significantly, it exhibits a promising generalization capability when applied to unseen and more complex image generation tasks. Our contributions can be summarized as follows. 1. We introduce multimodal instruction, a task representation that universally represents instruction from multiple elements, such as text, edge, mask, style, subject. 2. We propose to perform retrieval-augmented training and multimodal instruction tuning to adapt the pre-trained text-to-image models to follow multimodal instructions. 3. We build Instruct-Imagen, a unified model that tackles heterogeneous image generation tasks, surpassing several state-of-the-art models in their domains. More substantially, Instruct-Imagen generalizes to unseen and complex tasks without any ad hoc design. In the next section, we'll discuss the preliminary on diffusion models with input conditions. Then we'll introduce the format of multimodal instruction and discuss how prior image generation tasks can be unified in this framework. Diffusion models are latent variable models, parameterized by a set of parameters, in the form of a probability distribution. These models are trained to learn the image distribution by reversing the diffusion process. Theoretically, this reduces to learning to denoise a noised version of the input image into the original image, with a time-re-weighted square error loss. In the text-to-image models, the condition is often the embeddings of input text prompt, from pre-trained text embedding models. While multimodality information is necessary for extended image generation applications, there was not such a format in the literature that allows generalization. Therefore, we propose the multimodal instruction, a new format where language is used to explicitly state the objective behind tasks, with references to multimodal conditions. There are two key components in the proposed instruction format. 1. The payload text instruction that provides a detailed description of the task objective, with a reference marker. 2. A multimodal context with pairs of marker plus text and image. The model then employs a shared instruction understanding model to consume both the text instruction and the multimodal context, regardless of the specific modality in the context. This format represents various prior generation tasks, showing its compatibility to prior image generation tasks. More importantly, the flexibility of language allows multimodal instructions to extend to new tasks, without any modality and task-specific design. Section Summary. The introduction discusses the limitations of existing text-to-image models in comprehending complex instructions involving multiple modalities. To address this challenge, the authors propose a multimodal instruction approach that integrates information from different modalities, such as subject and style, to describe the objective of generating a customized image. They introduce their model, Instruct-Imagen, which is trained using a two-stage approach to process and follow multimodal instructions, resulting in contextually accurate and visually compelling images. The authors also highlight the generalization capability of Instruct-Imagen to unseen and complex image generation tasks. Section: Instruct-Imagen. In this section, we'll explain how our system, Instruct-Imagen, processes multimodal instructions and uses them for image generation. We'll also discuss our two-step training process for Instruct-Imagen. Instruct-Imagen is built on the concept of multimodal instructions, which are a unified way of representing previous image generation tasks. This allows the system to handle new and complex tasks. We've designed the model to extend pre-existing text-to-image diffusion models, specifically a cascaded diffusion model, so it can fully utilize the input multimodal instructions. Our version of Imagen, which is pre-trained on internal data sources, serves as the foundation for Instruct-Imagen. It consists of two parts: one that generates images with a resolution of 128 pixels from text prompts only, and another that scales these images up to a high-quality resolution of 1024 pixels. For the purpose of this work, we're only focusing on training and adapting the 128-pixel resolution text-to-image network. This model is a convolutional U-net with a bottleneck, paired with a downsampling encoder and upsampling decoder. The text is embedded with a pre-trained T5XXL model, and these embeddings are input to the downsampling encoder as a condition, and to the cross-attention on bottleneck representation as an enhanced reference. We've adapted the cascaded text-to-image model to encode the multimodal instruction by reusing the pre-trained text-to-image model as much as possible. We've only added one cross-attention layer that conditions the bottleneck representation of U-net with the embedded multimodal context. This increases the number of parameters in our model from 2.51 billion to 2.76 billion, which is about a 10% increase. Our training process is divided into two stages. In the first stage, we continue the text-to-image generation, with the addition of retrieved neighbor, image, text, pairs. In the second stage, we fine-tune the model from the first stage on a variety of image generation tasks, each paired with corresponding multimodal instructions. In both stages, the model is optimized end-to-end. One of the main challenges for Instruct-Imagen is training the model to condition on multimodal inputs for its generation. A simple approach would be to use naturally distributed multimodal internet data, such as Wikipedia articles with images, and train models to use the interleaved, image, text data to generate the desired output image. However, this often leads to the model ignoring the multimodal context. To address this, we use training data that allows the model to learn to look at the relevant but not duplicated neighboring multimodal context when generating an image according to the current text prompt. In the second stage of training, we prepared 11 image generation datasets for multimodal instruction tuning. These datasets cover 5 task categories: text-to-image generation, control-to image generation, subject-driven generation, styled generation, and style transfer. For each dataset, we used GPT-4 to generate 100 rephrased instruction templates with high variation, and manually check them for semantic correctness. In summary, Instruct-Imagen is a powerful tool for image generation that leverages multimodal instructions and a two-stage training process to create high-quality images from text prompts. Section Summary. In this section, the paper introduces Instruct-Imagen, a model that encodes multimodal instructions and leverages them for image generation. The model is based on a cascaded text-to-image diffusion model and uses a two-stage training framework. The first stage involves training the model for text-to-image generation with augmented neighbor pairs, while the second stage fine-tunes the model on diverse image generation tasks paired with corresponding multimodal instructions. Section: Related work. Let's delve into the related work and experiments conducted in this study. Firstly, we'll discuss instruction tuning. This concept was initially introduced in FLAN, a model that fine-tunes a large language model, LLM, based on instructions, thereby significantly enhancing its ability to learn new tasks without prior exposure. This approach was later expanded by Chung and his team, demonstrating its remarkable generalization across numerous natural language processing tasks. The instruction data is a crucial component in the fine-tuned LLM. This successful method of text instruction tuning was later applied to vision language models, allowing them to generalize across tasks like recognition and visual question answering. While other studies have explored image generation with multimodal inputs, our paper presents a fresh approach to investigate multimodal instruction tuning for image generation models. Next, we'll talk about controlled image synthesis. Recent advancements in text-to-image generative models have demonstrated impressive capabilities in various areas, such as creativity, photorealism, diversity, and coherence. A key aspect of these advancements is controllability, which has been improved by adapting these models to specific subjects, styles, masks, and so on. For instance, Dream Booth fine-tunes a text-to-image model on a limited set of images to better capture the nuances of a specific subject. However, a common limitation persists. These models often specialize in specific modalities, leaving the generalization to new modalities and their combinations unexplored. To address this, we introduce Instruct-Imagen, a novel model designed to understand complex relationships and generalize effectively to unencountered tasks. Now, let's move on to the experiments. We first introduce the experimental setup, the human evaluation protocol, and comparative baseline systems. We then present the main results, highlighting the advantages of Instruct-Imagen in tackling multiple in-domain tasks and challenging unseen tasks. We also perform an in-depth analysis to study the design of Instruct-Imagen and the model's failure mode. In our experimental setup, we evaluate our models with two setups, in-domain task evaluation and zero-shot task evaluation, with the latter being more challenging. We use the recently introduced conditional image generation benchmark, ImagenHub, for evaluating text-to-image generation. We also employ other datasets for in-domain evaluation. We compare Instruct-Imagen with three categories of baseline models: prior state-of-the-art method, single-task model, and multi-task model. Since no single prior model can handle all image generation tasks, we compare different prior methods on each task. For human evaluation, we follow the same evaluation protocol as before to conduct a systematic human study. Each sample is rated by at least 3 raters for their semantic consistency score, SC, and perceptual quality score, PQ. The final human score is defined as the square root of the product of SC and PQ. We recruit 8 human raters and train them following the guidelines in ImagenHub. Each method is evaluated independently, but we assign the same rater for samples generated by different methods given the same input to ensure evaluation calibrated per example. Section Summary. The related work section discusses the concept of instruction tuning, which involves fine-tuning a large language model, LLM, on instructions to improve its performance on unseen tasks. This idea has been successfully applied to both text and vision language models. The section also mentions controlled image synthesis, which focuses on enhancing the controllability of text-to-image generative models by adapting them to specific subjects, styles, and other control signals. The experiments section describes the evaluation setup, including in-domain and zero-shot task evaluations, as well as the comparison with baseline models. Human evaluation is conducted using semantic consistency and perceptual quality scores. Section. Main results. Our main findings show that our model, Instruct-Imagen, performs as well as or better than previous methods and baselines in both in-domain and zero-shot evaluations. This is illustrated in the main results figure. The breakdown of the SC and PQ scores is detailed in the appendix. Our results suggest that training with multimodal instructions improves performance in tasks with limited training data, such as stylized generation. This training also maintains effectiveness in tasks with abundant data, like photorealistic imaging. Without this type of training, our multitask baseline tends to produce lower quality images and less accurate text alignment. For example, in the in-context stylization example in the in-domain comparison figure, the multitask baseline struggles to distinguish style from subject and to replicate the subject in its generation. This is also why it scores 0 in the style transfer task. These observations highlight the importance of instruction tuning. Unlike many current approaches that rely on task-specific methods or training, Instruct-Imagen efficiently manages compositional tasks. It does this by leveraging instructions that combine the objectives from individual tasks and by performing inference in context. This means no fine-tuning is required, which takes 18.2 seconds per example. As shown in the zero-shot comparison figure, Instruct-Imagen consistently outperforms others in following instructions and in output quality. Moreover, when multiple references are present in the multimodal context, the multitask baseline model fails to match the text instructions to the references. This results in some multimodal conditions being ignored. These results further demonstrate the effectiveness of our proposed model. More visualizations are available in the appendix. In addition to our main results, we also conducted studies to explore the limits of Instruct-Imagen, to examine important aspects of its training, and to analyze its failure mode. We found that Instruct-Imagen can edit images when fine-tuned. We fine-tuned Instruct-Imagen on the Magic Brush dataset, which contains approximately 9,000 examples, for 10,000 steps. We then evaluated it on the masked image editing data by Imagen Hub. We report the results using the overall score, O, and the accuracy, which is the percentage of examples where SC equals 1. Our results show that once fine-tuned, Instruct-Imagen performs significantly better than the baseline method and also a method specifically designed for mask-based image editing. However, the fine-tuned Instruct-Imagen introduces artifacts into edited images, particularly in high-resolution outputs after super-resolution. This happens because the model hasn't learned how to accurately copy pixels from context to output, a task that is quite different from other tasks that Instruct-Imagen performs. We found that retrieval-augmented training aids generalization. We compared variants of Instruct-Imagen in terms of whether they underwent retrieval-augmented training. Our results show that this type of training is crucial for achieving superior empirical results in both in-domain and zero-shot evaluations. This supports our hypothesis that retrieval-augmented training benefits the representation and handling of multimodal context. One common failure mode of Instruct-Imagen is its inability to follow instructions in the generation when attempting more complex multimodal instructions with at least 3 multimodal conditions. In these cases, the model can only satisfy a subset of the conditions specified in the multimodal instruction. We also provide additional qualitative visualizations on more diverse and sophisticated multimodal instructions to explore the limits of Instruct-Imagen. We do not provide qualitative results on face generation due to lack of consent from the original dataset owner. In conclusion, we introduce Instruct-Imagen, an image generation model that understands multimodal instruction to accomplish a variety of visual generative tasks. It represents a significant step forward for general-purpose visual generative models, as it allows not only in-domain image generation, but also zero-shot image generation on unseen and complex instructions. However, Instruct-Imagen cannot handle image editing tasks in zero-shot. A key limitation is its lack of pixel consistency with input images, which prevents the inclusion of additional tasks like in-painting and image editing in the instruction tuning. This issue arises from the use of a cascaded diffusion model, which depends on a low-resolution model for crucial decisions like layout and object semantics. This low-resolution model struggles with both accessing high-resolution input details and reproducing them in the output, leading to artifacts in the generated image. Based on these observations, we believe that a promising future direction is to develop diffusion models that operate at the raw image resolution. Section Summary. The paper presents Instruct-Imagen, a multimodal instruction-based image generation model that achieves superior results in both in-domain and zero-shot evaluations compared to baselines and prior methods. The model demonstrates enhanced performance in tasks with limited training data, such as stylized generation, while maintaining effectiveness in data-rich tasks like photorealistic imaging. However, the model struggles with pixel consistency and artifacts in high-resolution outputs, hindering its ability to handle image editing tasks in a zero-shot manner. Section. Acknowledgement. We'd like to express our gratitude to Jiwei Deng, Jason Baldridge, and Nando De Freitas for their insightful review and valuable feedback on an early draft of this paper. We also extend our special thanks to Han Zhang for his contributions during the initial discussions of this project. Our appreciation also goes to Irina Bloch for providing a style image that we used in our evaluation. On a broader note, we acknowledge that text-to-image generation models, such as Imagen and Stable Diffusion, raise ethical questions, including the potential for social bias. Our model, Instruct-Imagen, which uses similar large-scale datasets from the web, is not exempt from these concerns. However, the training of Instruct-Imagen, which is enhanced by retrieval augmentation and multimodal instruction tuning, has significantly improved the control and attribution of images. This increased control can be a double-edged sword. On one hand, it could be misused for harmful purposes, such as generating deceptive images of individuals. On the other hand, it has its benefits, such as reducing the occurrence of image hallucination and enhancing the relevance of images to user intent. It also has the potential to benefit underrepresented communities by effectively generating images of lesser-known landmarks, foods, and cultural artifacts, thereby addressing the bias in AI systems. To minimize potential risks to the public, we plan to exercise caution when releasing our code and API. Our future work will aim to establish a framework for responsible use, balancing the advantages of research transparency against the potential hazards of unrestricted access, to ensure that our work is used safely and beneficially.